Okay, welcome back. This is lecture 17 in Aerospace 584 Guidance and Navigation. In this lecture, we'll be talking about Kalman filtering and its applications. Well, mostly applications because we saw Kalman filtering in the last lecture. So, as a okay, oops. So, just to review a little bit of the stuff that we have done in the last couple of lectures, I showed you how we can construct an optimal filter for a linear system shown here. So let me get this pen started. Oops. Oops. Yep, there it is. Okay, so we have a linear system shown here. And we have the input, measured input U, measured input U, and the measured output YK. And using the system dynamics matrices A, B, C, D, D1 and D2, we can construct an optimal filter, which is shown here. This is a two-step optimal filter, also known as the Kalman filter. The first step is a copy of the dynamics. And the second step is the data assimilation step, where we inject the measured output. The gain matrix KK is computed by propagating the covariance matrix. The prior state error covariance matrix is propagated by this equation. The gain K is computed by this equation. And finally, the posterior state error covariance matrix is given by this expression. Now, in this particular case, I showed you the derivation for this case, and A, B, C, D1, and D2 were constant matrices, but they don't have to be. Like I discussed in the previous lecture, you can just replace them by AK, BK, and so on. And the rest of the derivation remains exactly the same. So even if you have an LTV system, linear time varying system, where you know these matrices AK, BK, CK, and so on, you can construct an optimal filter which looks exactly the same. All the constant matrices are just now replaced by the time varying matrices AK, BK, CK, and so on. And this filter is still optimal in the case of a linear time varying system. And this block diagram shows what's happening in a filter. So filtering, like I discussed, is a two-step process. In the first step, we have a physics update shown here or shown here. This step basically takes a copy of the physics or the dynamics of the system and produces, whoops, no eraser, yes, produces the prior estimate of the state x state at step k plus 1, which we denote as x hat k plus 1 given k. By using the measurements yk plus 1 and the gain kk, which is given by the Kalman filter or the optimal filter, we improve our estimate, and the improved estimate is the posterior state estimate, and it's denoted by x hat k plus 1 given k plus 1. Now, so I showed you how you can construct the optimal filter for the LTV case, but what about nonlinear systems? So you may have a nonlinear system where the dynamics is given by this function f, and the output map is given by this function g. These are not linear. They can be linear, but we assume that they are nonlinear. We assume additive disturbances, additive process noise, and additive measurement noise. This is just for the sake of simplicity. Even more complex cases can be considered following the same steps that I discussed in the previous lecture. But anyways, just to keep things simple, let's just assume that the noise, the process noise, and the measurement noise are additive. So like I showed you in the previous slide, the first step, which is the physics update. So this is the physics update. It just takes the copy of the dynamics of the system and propagates the state. So that's what we are going to do. We are going to take the posterior estimate at step k. We are going to produce the prior estimate at step k plus 1 using the original dynamics of the system. We don't know what the noise is, so we don't use the noise in the estimator, obviously. And the next step is going to remain exactly the same. We are going to take the prior estimate and add to it the output error scaled by the gain matrix kk to obtain the posterior estimate at step k plus 1. Now this gain kk is going to be computed exactly as before. But before I go there, the output error, instead of having c x hat k plus 1 given k here, I'm going to use the exact output map to compute the output. So I'm going to use the exact dynamics of the system to propagate the prior state to the posterior state at step k plus posterior state at step k to prior state at step k plus 1. And I'm going to use the output map to go from the prior estimate at step k plus 1 to posterior state at step k plus 1. Now, what about the gain matrix kk? The gain matrix kk is going to be computed exactly as it was done before. We have the prior covariance update, we have the gain calculation, and we have the posterior covariance update. Now, these matrices depend on AK, CK, and QK and RK. Now, how do we compute those? Now, QK and RK are easy. QK is simply given by D1K, D1K transpose, and RK is given by D2K, D2K transpose. And the AK and BK matrices are going to be the linearized versions of the functions f and g. And the way you linearize them is you take the gradient of f with respect to x, x is the state, and you evaluate this whole thing at the current state estimate and the measured input. Similarly, the output matrix CK is given by the gradient of the output map with respect to x, and you evaluate this gradient at the current state, and that gives you CK. We assume that the G doesn't depend on U, so that's why we don't have the U here. So this you might have seen in your other courses, or you might have heard of this extension of the Kalman filter, and this is called the extended Kalman filter. Extended Kalman filter is basically the Kalman filter for a nonlinear system, but it's not optimal now because these covariance matrices which are propagated, they assume linear dynamics, and since we don't have linear dynamics, the gain k that is given by these equations is not going to be optimal for the nonlinear dynamics. It is optimal for the linear dynamics, but it's not optimal for the nonlinear dynamics, and hence the extended Kalman filter is not optimal for the nonlinear system. It's just a suboptimal filter, but it's easy to implement. It works. So it's a great useful extension for nonlinear systems. And we are going to be using, I'm going to show you maybe 2 examples at the end of this lecture of the extended Kalman filter. Okay, so that was just a review of what we did earlier. In this lecture, we are going to be focusing on a bunch of cases. We want to see how we use the Kalman filter to estimate states. The navigation problem is all about using the measurements to construct our current state. The state includes our position and velocities. That's what we are trying to get. So we need to construct, we need to see how we can use the Kalman filter to use the measurements how can we use the Kalman filter with the measurements to produce a state estimate. So first, I'm going to start with static estimation. By static estimation, I mean that the state x is not varying. The state x is always a constant. So that means that AK or A matrix is going to be is going to be the identity. So xk plus 1 equals axk equals just xk, which implies that the dynamics matrix is just going to be the identity. And all the cases that I consider, I'm just going to replace the A matrix by the identity. So there are multiple cases that we can consider. We can have multiple measurements coming from a single sensor. We can have single measurement or multiple measurements coming from a single sensor, or we can have multiple sensors, again, producing a single measurement, or maybe they may be producing multiple measurements. These are various, all of these cases are not necessarily distinct cases. They are, all of these can be considered as special cases of Kalman filter, but just to show you the distinction, I'm considering all these cases. So if you have single sensor, well, let's consider an example. Let's say you have a car going at some velocity v, and you are estimating you're trying to estimate its velocity. Now, what are the different sensors that you can use? Well, you can have a GPS. You can use the tachometer of the car, or I don't know, you can use radar somehow. I don't know how you can use radar. You can use all these different types of sensors. Oh, pitot tube, yeah, pitot tube. You can use a pitot tube, use some CFD or fluid dynamics pitot tube to get the velocity of this vehicle. And then you can get these, so these are different types of sensors that you can have. And you can also get multiple readings from these sensors, or just one reading from this sensor. So if you get just one reading, that's just going to be, we're just going to call that measurement Y. So this is going to be the case of single measurements. I'm going to write Y. These could also be indexed by time. For example, you keep getting these measurements at 5 seconds or 10 seconds, or asynchronously, which means the GPS might be giving you measurements every 1 second. Tachometer could be giving you these measurements every 10th of a second. Radar could be giving you measurements every 2 minutes. So you may have, Y could be a vector, like Y, oops, what happened? Nope, I don't want the right click. So Y could be, Y1, Y2, Y3, and all of these could be, you could be getting them at different time instants. So Y1K, Y2K, Y3K, so YK. Anyways, I'm just going around a simple, silly point. So if you have a single measurement and single sensor, Y is just like Y. If you have single sensors and multiple measurements, then you have a sequence of Y, like Y1, Y2, Y3, If you have multiple sensors, then Y is going to be like Y1, Y2. And then if you have this guy, then you're going to have Y1, Y2 at K equals 1, and then Y1, Y2 at K equals 2. Anyways, you get the point. So first, we're going to consider this case. This case is also called sensor fusion. So you have multiple sensors making one single measurement, and you want to find out what is the best estimate of the variable that you're trying to estimate. Okay, so sensor fusion. So suppose we measure the velocity. We have this car, and we measure the velocity using different methods. Like I said, pitot tube, tachometer, and GPS. Now the question is, how do we merge these measurements to get the best estimate of the velocity? So at some time instant, you saw all these measurements, you noted down all these measurements, and now which of those measurements is closest? Well, you don't know, obviously. So the next best question that we can ask is, well, how do we use these three measurements to produce best estimate of the velocity in some sense? So let's look at a simple example. Now consider the case where you have two measurements, Y1 and Y2 of a variable X. So you have a variable X that you're trying to estimate. It's a constant value, and you measure y1 and y2. For example, you're trying to measure the distance between these 2 points, and you use ruler 1, that gives you y1, and you use ruler 2, that gives you y2, and then you ask ruler 1 and ruler 2, and then you ask which of these measurement, or how do I combine these 2 measurements to produce a better measurement. So anyways, what we are trying to do is we're trying to find out what is the best estimate of this variable x. Well, when we say best, we are obviously optimizing something. And in this case, we are going to optimize this cost function. Now, this cost function j is a function of x. X is what we are trying to produce. And we are going to minimize this cost function. So we are going to minimize alpha 1 times y1 minus x. So that's the error in the first measurement, plus alpha 2 times y2 minus x squared. That's the error in the second measurement. So we're going to minimize these, the sum of these 2 errors. This is also called the least squares because we take the squares of all the errors and we try to leastify it or minimize it. Now the minimizer of this cost function j satisfies this equation, that is the gradient of the function j at the minimizer should be equal to 0. This is just from high school calculus. So when you do partial j partial x of this equation, you can obtain this equation. And when I set this equation to 0, I get this equation. And when I solve this equation for x star, I end up getting this equation. So the x star, which is the best estimate of the variable x using measurement y1 and y2, is basically given by this equation. So x star is alpha 1 over alpha 1 plus alpha 2 times y1 plus blah, blah, blah. Anyways, a couple of things to note here. So the first thing to note here is that the weights actually add up to 1. So the weight of the first measurement is alpha 1 over alpha 1 plus alpha 2. And the weight of the second measurement is alpha 2 over alpha 1 plus alpha 2. So if I add these 2, I get 1. So they add up to 0. They add up to 1. And since they are positive, well, they have to be positive. All the weights need to be positive. I should have said that. Alpha I need to be greater than 0, because otherwise your cost function will become negative. We don't want negative cost functions. So anyways, both the alphas, if you add the weights, they add up to 0. And the second thing is that the weights of weights of the measurements are actually between 0 and 1. Alpha 1 and alpha 2. So alpha 1 and alpha 2 are not the weights. Alpha 1 over alpha 1 plus alpha 2 is the weight. So yeah, you got to be a little careful about that. So they are between 0 and 1. I think they are inclusive. Yeah, I can actually add those because I choose alpha 1 and alpha 2. Oh no, I said alpha 1 and alpha 2 are greater than 0. So this cannot be 0. Okay, so closed. Anyways, so the question is, how do we get alpha 1 and alpha 2 now? So alpha 1 and alpha 2, we chose these weights. So we are actually free to choose these weights. Now, we have to choose these weights judiciously. And usually what people do is they try to use the noise characteristics of these sensors to set these weights. So we saw in the equation y1 equals x plus w1 and y2 equals x plus w2. These w1 and w2 are the noises. So if the magnitude of the noise w1 is large, obviously we would want to weigh it less. Now, how can we capture that numerically? So if the magnitude of w1, or if the magnitude of the noise in the first sensor is large, then the variance of that sensor is large. So we can set alpha as the inverse of that variance. So variance is the square of the standard deviation, sigma. So we can just set alpha to be inverse of sigma squared, and that would give us the best estimate by this equation. And if we write this out completely, we can see that the weights are given by these two ratios. These are not inverse ratios, but these are like weird ratios. Um, the factor that multiplies y, one depends on the variance of the second sensor. But that's only because how these inverses work out to be. Anyways, you see the point. The best estimate is given by this equation, and this method can be extended to any number of sensors. So if you had n sensors, each measuring the variable x, then the best estimate of x is actually given by this expression. This is again, this is a weighted sum of all the measurements, where all the weights, it's the weighted mean, where all the weights are the inverses of the variances of each of those sensors. Okay, so that's one of the ways you can produce an optimal static estimation. Well, let's see if you can, we can do something else. Okay, now we are going to use a little bit of probability. In the previous case, everything was deterministic. You had one measurement, you chose the weights, and you produced the best estimate. There was no noise involved. So now we are going to use a little bit of probability to see if we can do better, or do we get the same results. Anyways, we get the same results, but we'll see how. So in this case, in the probabilistic case, we are going to model the measurement as a random variable. Now, what do I mean by that? Well, what I want to do is that I want to model the measurement y as a normally distributed variable with mean y bar, or the expected value phi bar, and the covariance sigma squared. So what do I mean by that? Let's say you're driving and you're going at 60 miles an hour, and you record your speed every second, and you keep recording that. You're going at 60 miles an hour. Somehow you know that the car is always going at 60 miles an hour. And then every second you keep recording your speed, looking at your dash. And then sometimes you're going to see 57, sometimes you're going to see 59, sometimes you're going to see 58.2, sometimes you're going to see 62. Obviously, you're not going to see 60 all the time. I mean, real life experience you must have seen, it just doesn't stay exactly at the speed, but it keeps going back and forth. 65, da 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 da. And if you plot out a histogram, you're going to basically see that it looks something like this. It's going to be centered at 60, and you're going to have errors on both sides. And there's no reason to believe that the errors are going to be higher on one side. Actually, there are, but let's just assume they are not. So this type of distribution, this is very closely a normal distribution or a Gaussian distribution. So we are going to assume that our speed is normally distributed around our true speed, which is 60 miles per hour. Now, how does this, well, it's not like you just somehow can know that you're driving at 60 miles an hour. You can actually use your measured data to estimate what this mean looks like. And to do that, we use Monte Carlo method. Monte Carlo method, I mean, they sound fancy, but it's just about taking means. So y bar, which is the expected value of y, is equal to this limit. Basically, what it's saying is that this can be approximated by 1 over n, which is a running mean of the measurements. And similarly, you can find the standard deviation, the variance of your speed, which is the covariance of y, which is defined as the expected value of y minus the mean squared. And it's going to be it equals this limit. And this can also be approximated by simply taking a bunch of variables, bunch of measurements, and then evaluating this expression, yi minus y bar squared. Y bar, you just calculated in the previous equation. So if you do this experiment and then you look at all these data points, you're going to see that you end up with a histogram which looks like this. And then you can use that histogram to calculate y bar and sigma squared. So using these data points, we can say that our velocity, which is a random variable, which is modeled as a random variable, is modeled as a Gaussian random variable with expected value y bar and the variance sigma squared. Okay, now let's say we have a bunch of these values. What do we do? How do we produce a better estimate of a variable when we have measurements from sensors which are distributed per this distribution? So let me get more specific. So suppose that we have two sensors, y1 and y2, and each of these sensors is modeled as a random variable which is distributed as shown here. Both of these are Gaussian distributions. The first sensor has the mean or the expected value y1 bar. Its variance is sigma 1 squared. And the second sensor's expected value is y2 bar, and its variance is sigma 2 squared. Now, what we want to do is we want to construct a random variable given here. It's a linear combination of y1 and y2. It's actually a convex sum of y1 and y2. Convex sum is just a sum of two quantities or n quantities where the weights add up to 1 and all of the weights are greater than 0. So beta is greater than 0. And the sum of these weights add up to 1. We want to construct a random variable given by this equation with the smallest possible variance. We know the variance of y1, we know the variance of y2. We want to find out a combination with the smallest variance. And to do that, well, we have to go through all the steps to calculate the covariance. So first, we need the expected value of x. Expected value is a linear operator. So the expected value of x is just given by this equation. So this is pretty easy to use because beta times expected value of y1 is just beta times y1 bar, and the same for y2. So this equation is pretty easy. The second step is to calculate the covariance of the variable x. And the covariance of the variable x is defined by this equation. The expected value of this expression, and when you expand this out, you can see that the covariance actually satisfies this equation. And now expected value of x, I know what that is, and then I just take the square for this term. And the expected value of x squared, again, I just replace x squared with the expression for x, expand the square like so. And then when I take the expected value operator inside, I can pull all the constants out, and using the linearity, I can get this expression. You should stop the video and look at this expression to make sure that I get all the terms correctly. So So that's the final expression. So that's the covariance of x for our convex sum of random variables y1 and y2. Now we can actually simplify it even further. We use the fact that the covariance of y1 is sigma 1 squared, and that sigma 1 squared actually, using the definition of covariance, is equal to this term. And similarly for sigma 2. And finally, assuming that y1 and y2 are independent, and if they are independent, then the expected value of y1, y2 is simply the expected value of y1 times the expected value of y2, which we know as this. And independent just means that they are two different sensors, and the reading on one sensor doesn't affect the reading on the other sensor. So if you're using a GPS and a radar to calculate or to measure the velocity, there's no reason to believe that one is going to affect the measurement of the other. So they're pretty independent. Anyway, so we go back with these simplifications or these equations, and we can simplify the covariance of X equation, and we end up with just this tiny little thing. That's it. The covariance of X is actually given by this expression. And since we are trying to minimize the covariance of X, is this even recording? Yes, it is recording. Anyways, so if the cost is simply given by this equation, and I'm going to minimize this cost with respect to this variable beta. This is a single variable function, and you use single variable calculus to minimize this cost g. And again, by setting the derivative of j with respect to beta to 0, I find that beta star is given by this. So this expression, this weight, beta square, is given by beta star. And of course, the 1 minus beta is going to be given by, sigma 1. 1 minus beta star is given by sigma 1 squared over sigma 1 squared plus sigma 2 squared. Okay, so we are already seeing that we are getting expressions which are similar to the case, similar to the expressions we got in the previous case. So let's keep going. We know the weights are the X is going to be given by beta 1 y1 plus beta 1 y1 plus 1 minus beta. Well, there is no beta 1. They're just beta y1 plus 1 minus beta y2. And when I replace beta and 1 minus beta, I get this as the expression. And this is exactly the same expression that I got in the different interpretation, in the previous interpretation that we just talked about. And if we take the expected value of this expression, since these weights are constants, we simply get y1 bar, a convex sum of y1 bar and y2 bar. And the minimum covariance, the minimized covariance, is given by this expression. And this, you can obtain this by substituting beta star in, I think, j of beta. I think it was beta square sigma 1 square plus 1 minus beta square sigma 2 square. And when you substitute beta star in this expression, you end up with this expression. And if you look at this closely, you find that this is actually the inverse of the sum of inverses, which is called the harmonic mean. So the covariance of X is the harmonic mean of the variance of the first sensor and the variance of the second sensor. And it's just a fact about harmonic means that the harmonic mean is smaller than both the harmonic mean of two numbers is smaller than both the numbers. So covariance of X is going to be less than the smaller of sigma 1 squared and sigma 2 squared. So yeah, one of the observations to make here is that no matter how bad your sensor is, so no, let me start again. So let's suppose you have two sensors. First sensor is very, very good, which means sigma 1 is very small. And then the second sensor is very bad, which means sigma 2 is much, much worse than sigma 1. Even when you combine, so what this is saying, what this, all the stuff that I've been showing you is saying is that even when you combine this very bad measurement with this very good measurement, your variance of the new estimate is going to be smaller, which means the accuracy of your estimate improves even with bad sensors. So you should be using as many sensors as you can. Okay, so next we come to the Kalman filter interpretation of the static estimation. So I've shown you the Kalman filter I showed you the Kalman filter in last lecture, also in the review in the beginning of this lecture, but we haven't really applied Kalman filter at all, even once so far. So let's let's see how we can apply the Kalman filter to do the same, to solve the same problem that we already have solved twice. So this is an overkill, but it serves a good purpose in the sense that it shows us how exactly what Kalman filter is doing. So on the left here is again the Kalman filter for a linear system, time-varying linear system. We have the system, we have the estimator, and the gain matrix computation. And since we are dealing with a static estimation case, I'm going to assume that A is equal to the identity and C is also equal to the identity, which means that we are only worried about improving our measurements. There is no internal dynamics going on. We can see the entire dynamics because we are measuring the entire dynamics. So anyways, the estimator for this system looks like this. This is exactly these two equations, 1 and 2, just the A and the C matrices have been replaced by the identities. So anyways, we get the optimal or the Kalman filter for the static estimation case on the right hand side. The P matrices and the gain matrices are computed, are shown. No, the gain matrix. Oh my God. The covariance matrices and the gain matrices are computed as shown here. Okay, so let's look at a very simple example. So in the previous two interpretations, we had two measurements of one variable. So we are interested in a variable X, and we have measured it twice using two different sensors. Okay, let me start writing down. One to measure X. And we have two sensors, sensor 1 and we have sensor 2. So now I'll show you how we can use the Kalman filter to produce a good estimate of X using the measurements Y1 and Y2. Okay, so these equations are exactly the equations that we saw on the previous page. We have the true system. Well, I shouldn't call it the true system. I should call it the model. This is our model. The dynamics is static, and we have a full state measurement, and the measurements are corrupted by the measurement noises. We have the Kalman filter, and the Kalman filter in this case can be written as this equation, and you see what's happening here. The estimate at step k plus 1 is, again, a convex sum of the prior estimate and the measurement. And the gain k is given by, of course, the Kalman filter. And for the scalar case, where A is equal to 1 and C equals 1, the pk, the kk, and the posterior covariance matrix are computed by these three equations. So let's see what's happening. We have two sensors. So initially we have some estimate of what our variable is. Let's just assume that we have some. I haven't shown you what that should be, but let's just assume that we have one. Using the dynamics, which is nothing, we can calculate the prior estimate, and using the first measurement, that is the measurement from sensor 1, I can compute the posterior estimate. So this posterior estimate, this first estimate has been obtained just by using the first measurement. And then I can pass this through the second copy of the Kalman filter. So these two blocks is one implementation of Kalman filter. The second two blocks is the second implementation of Kalman filter, which is going to assimilate the sensor 2. Anyways, so I have a posterior estimate after the first measurement, then I'm going to pass it through the physics, and then I'm going to pass it through the assimilation step using the measurement 2, and that's going to give me my final estimate. So using the measurements Y1 and Y2, we have obtained our posterior estimate. So since we only have two measurements, we only do it for 2 steps, and the posterior estimate as step 2 gives us the estimate of the variable x that we are looking for. Okay, let's look at these equations involved, and it is a horrible mess. But let me walk you through these equations slowly. So this part is just what you saw earlier, so you can ignore this part for now. Okay, so the prior estimate, let's suppose the prior estimate for somehow you knew what x bar was. If you didn't know anything about the initial estimate of the variable x, you can just set that to 0. Usually people just set the initial estimate to be 0. And we assume that the initial estimate, the initial covariance of the estimate is p bar. Now, if p bar is large, it means that the variance of the estimate is large, which means we don't really have much confidence in our initial estimate. If p bar is small, it means that we know that our estimate is concentrated around whatever x bar value you chose. So that means we have high confidence in where it is. But usually in this interpretation, I'll show you that we really want x bar to be 0 and p bar to be a very high value. Anyways, using this p bar, we can calculate what k naught needs to be, what the posterior estimate is going to look like at step 1, and the posterior covariance at step 1 is going to be this. And using x hat 1, 1, I can calculate what x hat 2, 1 is going to be. You can follow all these equations. I think they're right, but if you find an error, let me know. But I don't think there's an error because I reached the result that I wanted to reach. Anyways, the gain K1, again, repeated application of the same formula gives me this expression. And using this expression of K1, I compute x hat 2, 2, which I'm after. And x hat 2, 2 is given by this expression. And after a little bit of algebra, it's going to be a sum of these 3 terms. So you can see it is x hat 2, 2 is basically, actually it is a convex sum of x bar, which is our initial estimate, the first measurement, and the second measurement. And the covariance at step 2, variance at step 2, is given by this expression here. This is pretty much the same result that we got in the previous case. So basically what I'm doing is I'm showing you multiple logical steps that you can choose to employ to get to basically the same result. So if you look at the x hat 2, 2 and the p22 equation carefully, and then you see what happens when p bar goes to infinity. If p bar is a very large value, which means you have 0 confidence in your initial estimate, your x hat 2, 2 approaches this value, and the covariance, state covariance, posterior state covariance reaches this value. You can sort of see that, well, not sort of, exactly, that if you replace R1 by sigma 1 squared and R2 by sigma 2 squares, which by the way are exactly what the physical meaning of R1 and R2 is. R1 is the variance of the measurement noise of the first sensor, and R2 is the variance of the measurement noise of the second sensor. You can see that this is exactly the same result that we got by deterministic minimization, probabilistic covariance minimization, and now with the Kalman filter. And you're supposed to get the same result because Kalman filter is the optimal filter which minimizes the covariance of the posterior state error. Anyways, looking at this equation, you can see that this is actually equal to 1 over R1 plus 1 over R2 square, no square, inverse again, which says that the covariance of the estimate is the harmonic mean of the covariances of both the sensors. This is only the case when p bar is infinity. If p bar is not infinity, then basically what a finite p bar and a non-zero x bar is saying is that you basically, okay, this is tricky. So if I have a non-zero X bar and a finite, whoops, finite P bar. It's like having another measurement with this is equal to measurement X bar with variance P bar. So now instead of combining two measurements, I'm just combining three measurements where the third measurement is X bar and its variance is P bar. So Kalman filter is exactly giving you what it's supposed to. Anyways, let's look at more cases. So now we are going to focus on this case, which is a single sensor producing multiple measurements. Now, since it's a single sensor, the RK is going to be constant. Actually, I don't remember what example I have, so we'll see. But anyways, this could be the case where you have you're driving a car, you're looking at your pitot tube, and it's continuously producing a bunch of measurements, and you want to produce a single good estimate from those measurements. There are multiple things that you can do, but let's see how we can apply Kalman filter to get a good estimate. So yeah, so we're considering the same example. We're going at 60 miles an hour and we record our speed every second. So we have one sensor, one speed sensor, one speed sensor producing measurements. So our model is going to be given by these two equations. The state X is the speed because the speed is constant. The model says that xk plus 1 is just xk. And since we are measuring the speed with some potential noise, our measurement is going to be given by this equation. We can construct the Kalman filter. The filter is given by these two equations. The physics update and the data assimilation with the P and the K matrices given by these three equations. Now, yeah, one thing to note is that you have a sensor, and that sensor is going to give you, the sensor has some specification. It produces a mean, it produces all its value around a mean, and it has some standard deviation sigma square. And just keep note of these two things because we'll be using these two. So let's suppose the sensor is producing, actually it's messed up. So I assumed X, the true value of X is 1. So forget 60 miles an hour. So just assume that the true value is 1, whatever unit, 1 mile per hour. And we are trying to use a sensor which has a variance of 0.01 to get an estimate of this measurement. So we are going to assume that our measurement is normally distributed around 1 with a variance of 0.01. And we are going to implement our Kalman filter, which is the two equations I showed you in the previous slide. And this is what happens. The first plot shows the posterior estimate at each step. And we see that the estimate immediately goes to near 1, and then hovers and gets closer and closer and closer. And it's almost closing at 1. But this has taken, what, 10 to the 5 steps. This is the log scale. Both of, not both, actually. The y-axis is linear, the x-axis is log. As time goes on, as you get more and more data, you actually converge to the expected value, which is 1 in this case. The expected value of y is 1. Okay, so the expected value is converged to 1. What about the variance? Now, the variance of the estimate X is shown here. It actually is continuously decreasing. Now, note that the variance the variance of y is sigma squared. It's a constant. It's 0.01 in this case, 0.01. But the covariance of the xk keeps decreasing, and it actually goes to 0, which means that the estimate of your speed keeps on improving even though your measurement is noisy. And I mean, this result we already saw in the previous lecture, that the covariance matrix goes to 0. But anyways, in this particular example, we can clearly see how it goes to 0. What is this kink right here? So if you see closely, this is actually 10 to the minus 1. So before the covariance of your state is larger than 10 to the minus 1, in that case, your measurements are going to be a better source of information. So each measurement that you get drops your covariance a lot. But once your covariance of the state drops below 10 to the minus 1, then your model actually is performing better because your measurements are coming with a covariance of 0.01. Actually, shouldn't this be 0.02? No. There must be an error because I do remember setting it to 0.1. Actually, it is possible that in the simulation this was set to 0.1, not 0.01, because this kink occurs at the value of RK. Anyways, in this region, your state estimate is better. State estimate is better. And that's why the covariance gets the covariance decreases slowly. And in this region, your measurements are better. Actually, the measurements are not better. It's the sensor which is better. So sensor is better. Oh my God. Okay, go back. Sensor is better. Okay, so this is how you can use the Kalman filter to produce a good estimate of a variable using multiple measurement of that variable from a sensor. So there are a couple of things that I want to note. I mean, we saw those things in the from the example, but we can see those things from these equations also. For the case where we have one sensor producing a sequence of measurements, we can use the Kalman filter to produce a good estimate of the variable. The K matrix and the P matrices are given by these two equations. Now, a couple of things to note here. First, we know that this is the harmonic mean of 1 over PKK and 1 over RK plus 1 inverse. So the covariance PK, the posterior covariance PKK is always greater than 0, and PK plus 1 given K plus 1 is always less than these guys. So PK, the posterior covariance is always decreasing, which means that the posterior covariance is going to go to 0. Well, this is not very surprising. We already saw this the last time. The other thing to note is the gain matrix. So look at the gain matrix. We have PKK divided by PKK plus RK plus 1. Now this guy for a single sensor is going to be a constant. And if PKK and PKK go to 0, then this gain matrix KK is going to become 0. Now gain KK is what is weighting the output error. Now if KK goes to 0, your filter is basically ignoring the measurements completely. And this is one of the big problems in Kalman filtering. As your estimate gets better and better, your filter starts ignoring the measurement. And since these KK computations don't depend on the data, they only depend on whatever you chose PK for and what your C matrices, A and C matrices are. Your filter actually switches itself off There are few solutions, ad hoc solutions to this problem. We can use something called as the forgetting factor. I don't want to get into the forgetting factor. That's a whole big thing, but that's one of the solutions. The other easier solution is called the covariance resetting. And what you do in covariance resetting is that we, after every so much time, we just set PKK to be a large value, or whatever the initial value of PKK was. So after every few steps or time period, we are going to do basically this. So PKK is going to a small number switching off, and when it goes below a threshold, P threshold, you just set it to pull it back to the original value. So that is one way of keeping the filter alive. And also, we can see from this equation that the PK, I'm sorry, the factor which is multiplying the PKK, which is given by this equation, and the fact that PKK is going to 0 implies that this whole factor is going to 1, which means that the covariance matrix is going to decrease ever more slowly. And we actually saw that in the previous plot. I didn't point it out, but I should point it out now, that you can see from the second part that the slope is a constant, and both of these scales are log. So you can see that the error drops from 10 to the minus 2 to 10 to the minus 4 in about 10 to the 1 to 10 to the 3 steps, which is 1000 minus 10. So this is 990 steps. Now, to drop the error by 2 orders of magnitude again, let's say going from 10 to the minus 4 to 10 to the minus 6, we actually need 100,000 minus 1,000, which is 99,000 steps. So the same drop now takes far more data to produce a better estimate. So that's why we say that the rate of drop of the covariance gets slower and slower and slower. So it does go to 0, but it goes to 0 ever more slowly. Okay, so now we are going to do something more useful. I'm going to consider the problem 3 from homework 1, position fixing, I think we called it. Okay, so let's look at it. So we want to do position fixing using Kalman filter. I'm going to try to use the same notation as Professor Bernstein's notation. This is a notational mess, but you will see. But I'll try my best to keep things as clear as possible. So we start with this problem. So let's suppose we have some of these beacons, and we know the position of these beacons. So the beacon Li has a position xi, yi. We have a map, and we know where the beacon Li is. So let me make a picture. So let's say we have a beacon there, a beacon there, and a beacon there. So we have these 3 beacons. And let's say the distance from this beacon, let's say the distance that we measure from this beacon, from the beacon Li, is Ri. So for example, if I measure Ri from R1 from L1, this is going to be R1, then I can be anywhere on this circle. And then if I measure R2 from beacon 2, then I can be anywhere on this circle. So these 2 circles are going to intersect here and somewhere here. So I need one more beacon. So now let's say I have another measurement, another distance from a beacon L3. So that's going to give me this. And then I can see that we can calculate that I'm at this point. Okay. So I'm going to assume that my measurements, now I'm going to call the big Y the measurements, because the small x and y are now used to denote the coordinates of the beacons and our position. So this is going to be position P that we are looking for. So we can measure R1, R2, R3, and our goal is to find the position X, Y. We know what the position of beacon L1 is, which it's X1, Y1. We know the position of L2, it is X2, Y2. And similarly, we know where L3 is, it's at X3, Y3. We measure R1, R2, R3, and we get we want the position of, we want our position, which is X, Y. So each of these beacons is going to satisfy this equation. This is just saying that wherever our sensor is, it's going to satisfy this equation. It's going to lie on this circle. Okay, so each beacon, with each beacon, we are producing one distance measurement, and our distance measurement is given by this equation. We don't know X, we know what Xi and Yi is. Xi, Yi, again, is the location of the beacon Li. So we need at least 3 measurements to produce a unique value of X and Y. So I'm going to write my measurement vector Y. It's going to be a 3x1 vector. It's going to be Y1, Y2, Y3, and it's going to be given by this big matrix. So I'm going to call this big matrix G of XY. G is a function. This function G is shown here, and it's a function of X and Y. X and Y are these guys. Not the data. These are the X and Ys that we are looking for. And then I'm going to call my state X. I'm just going to define the state X as the small x and small y, which is the state, which is the position coordinates of our sensor that we're trying to estimate the position of. Okay, so this is our model. Our state, which is the coordinate of the sensors, is not changing. So xk plus 1 is just given by xk. My state is given by big X. And my measurements are going to be given by this equation. G is the function that I defined in the previous slide. And I'm going to assume that all these 3 measurements are going to be noisy. D2 is going to tell you what the noise characteristic in each of these measurement is going to be. So using the extended Kalman filter that I showed you in the second or third slide, we can write down the filter equations. We have the dynamics part, we have the assimilation part, and the PK plus the prior covariance, the gain matrix, and the posterior covariance matrices are given by these 3 equations, which you've seen multiple times now. Now, the A is just the identity in this case. AK is just the identity, so that part is easy. Of course, QK is also 0 because the model is exact. We don't have any process noise. The output matrix CK is going to contain 3 rows, C1, C2, C3. And each of these rows is given here. CI, small ci, is given by the partial GI. GI is the first, second, and third component of the function G that I showed you on the previous slide. So we take the gradient of each of these functions with respect to the state. State is big X. Big X has the variables X and Y. So I'm going to take the derivative with respect to X and Y, and then I'm going to stack them up in a row vector. And this equation is going to give me the CK matrix that I'm looking for, that I'm going to use in my filter. Now note that CI depends, CI is given by this expression, and in the denominator I have these 2 guys. So if X hat K equals Xi and Y hat K equals Yi, then this whole thing is undefined. So all we have to make sure that we do not estimate X hat K and Y hat K. Oh yeah, what is X hat K and Y hat K? X hat K and Y hat K is the estimate of the position of our sensor at the kth step. We just got to make sure that these are not at any of the beacons, which is easy because we know where the beacons are. So we just have to make sure that our initialization of our filter is not at the beacons. So if we are not at the beacons, this guy is always going to evaluate to be something greater than 0. Okay, so let's see what happens. We have these three beacons, L1, L2, L3. I use the same numbers that were in your homework. And I'm going to start my Kalman filter at 4.4. This is my initial estimate. And I'm going to assume that my true location is this. And this is what is used to generate the data, Y1, Y2, Y3. It's corrupted by a noise, I think, with the standard deviation 10 to the minus 1. Yeah, this should be 10 to the minus 1. I didn't expand the scales. But anyways, as you can see, Kalman filter produces an estimate. I set P naught to be 100, I think, in this case. P naught is 100 times the identity, because there are two states. We are estimating two variables. So P naught is going to be 2 by 2 matrix. So we get this sort of behavior. And see, the estimate actually gets pretty close to the true value in just 3 or 4 steps. This is the second, this is the third, and you're very close to your true value. Now, these two plots show the estimate and the covariances. The estimate, actually, I have the hats backwards. So this should be the hat, and there should not be any hat here. Anyways, so this is shown on a log scale. So we close into the true values pretty quickly, and then we stay there as more and more measurements come in. We actually keep getting closer and closer to the true value. The estimate covariance also keeps on improving. The same behavior as before. We have a little kink before the estimates covariance is greater than, no. This moment shows the instant at which the covariance of the state estimate gets better than the measurement noise. Actually, you know what this step is. This step is always 2, because we know as soon as we add an estimate, add a measurement, our state variance is going to be smaller than the initial variance. It's going to be smaller than the harmonic mean of the initial variance and the measurement noise. So exactly at k equals 2, I'm going to drop below the measurement noise. So anyways, that's why you have the big drop in the beginning. And then this is the natural curve. Not natural curve, but this is the way the covariance drops in Kalman filter. Almost in all cases, you will see the same behavior. Anyways, you can do the same experiment with a bunch of different values of P naught. And if P naught is very, very small, then what's going to happen is that this means that we are very confident in our initial estimate of the position, very confident in initial estimate. So we are going to use the measurements. Of course, we are going to use the measurement and improve our estimate, but it's going to be very, very slow. You see almost all the data points very slowly go along this trajectory. But if P naught is very high, which means that no confidence in our estimate, in our initial estimate, we are basically going to react very strongly to the measurement. We are going to make huge jumps, and then we are going to immediately lock into the true values. And yeah, so high P naught is going to go through high transients, quick convergence, and the low P naught is going to go through low transients, but very slow convergence. So it really depends on the application, which type of, what behavior of the estimate you want. Okay, so in this lecture, I showed you how you can use the Kalman filter to solve the problem of static estimation, and showed you an example of position fixing that you already saw in one of your homeworks. And in the next lecture, I will show you how we can use the Kalman filter to solve the navigation problem where the object of our study is moving, it's not static. So we are going to include some dynamics, and we are going to probably see a few simple cases where we have very simple motion, and we are going to try to use the Kalman filter to track that motion. That's it for this lecture. Thank you so much.